Hi everyone. Yeah, this is Dr. S. Venkateswarlu, working as a professor of C at IARE, Hyderabad. Yeah, today we'll discussing about uh, Parks-McClellan algorithm to design an FIR non-recursive filter. Yeah, in this case, use the Parks-McClellan algorithm to design an FIR bandpass filter of order. It is given. Order is what you call 70. The order is specified 70. Specify the normalized stop band frequencies of 0.3 pi and 0.7 pi radians per sample and normalized, okay, and the normalized passband frequencies of which is given 0.4 pi and 0.6 pi radians per sample. So this is the given data. Plot the ideal and actual magnitude responses with the help of this Parks-McClellan algorithm to design an finite impulse response or non-recursive filter, which is based on a band pass filter of order 17. Now here it is f is equal to this first, where a is equal to like this, b is equal to FIR m of that order of the filter is 17. That given f value like 0, 0.3, 0.4, 0.6, 0.7 and 1. Okay, and here h of omega is equal to the frequency z of p comma 1 comma 512. Okay, so plot f comma a comma w by pi and radius of h less than the ideal FIR thing for design. Okay, x label is radian frequency omega pi and y label is magnitude. Okay, we will expect this all output response. The red color all are ideal, where what do you call radical is FIRPM design, Parks-McClellan design, and blue color is ideal. So radian frequency versus magnitude response we will expect. This role by using the Matlab software. By using the Matlab software, we should write a piece of code like this. After that, execute this run this program. We will expect this all. Okay. So coming to this here, Parks-McClellan low pass filter. Try this example using this all. The code is so based on the design. Design a low pass filter with 1500 Hz, pass band cutoff frequency 2000 Hz, stop band cutoff frequency. Specify the sampling frequency of 8000 Hz and require the maximum stop band amplitude of, okay, so 0.01. Okay, like this it is specified. Okay, now so to obtain required filter order, normalized frequency and edges frequency band amplitude and weights using the FIR mode like this. We are following by using this all this link. We will expect the more problems on this. Parks-McClellan low pass, high pass, band pass, and band elimination, and so on. Okay, so for this it is designed. We will expect this all magnitude response, normalized frequency into magnitude like this. This is the output response while we are using Parks-McClellan low pass filter. So Parks-McClellan algorithm and Remez algorithm. Here it is specified what you call Parks-McClellan method. So often called Remez exchange method. Okay, so this method begins on the optimal linear phase filter directly from the design specifications. This is the standard method for non-recursive filters like finite impulse response distant filter design. So in Matlab, this method is available as a remez of. Okay. So with this, so approximation errors. That approximation errors from the theory of the Fourier series. We got the stuff this. After this, so rectangular window is design method with truncation of the impulse response. Okay. So given the best mean square L2 approximation, so to a desired frequency response for a given filter design M. With this given filter length is like this, we will expect. Okay, the given filter is length M. Okay, graphically I have to place this one. So Minimax design. Coming to the Minimax design, however, simple truncation leads to a adverse behavior near discontinuities and in the stop band. So better filter generally results from the minimization of the maximum error, okay, well, infinity or frequency weighted error criterion. For the Minimax design purpose, we require this all okay, desirability. Okay, we will explore the optimal design if you are in low pass filter. Optimum filters, they consider the linear phase finite impulse response filter for which that impulse response h of n is equal to h of minus n. Take Fourier transform of that, we will expect this all after applying this Fourier transform. So now v terms cos omega can be expressed as polynomial of degree n in the cos omega. Now coming to the linear least mean square error filter design. So FIR filter design by optimization, least square method is required. So our expectation, our task is FIR design by optimization. For that case, we will use least mean square method. We now present the method that approximates the desired frequency response by a linear phase finite impulse response amplitude function according to the following the optimality criteria. Optimality criterion. So the difference between the ideal filter here somewhat it is the least square design of a FIR filter meeting the specifications is not guaranteed. The prior trial and error is often required for designing this type of methodology for variation with optimum finite impulse response filter. It might be useful to set the transition band slightly narrower than the needed, and it is often necessary to experiment with the weights. Occasionally, the resulting frequency response may be peculiar. Again, changing the weights would help to resolve the problem. Design of FIR finite impulse response differentiators. So there is a types of filters. One is these types of filters are easy to design with the standard Remez algorithm. So low pass, by using the low pass, because of it allows only low frequency components, it opposes the high frequency components. And coming to the high pass filter, band pass, band stop, and multiband, and arbitrary magnitude, and so on. Okay, for this, in Matlab may need to use the Hilbert or switch for some filters. These are all why we are choosing this design of FIR filter, because of the output response. While you are using the non-recursive filter, output response should be what you call optimal. The time we have to choose the different types of filters. These types of the filters are easy to design with the standard Remez algorithm. Okay, we have to follow that standard Remez algorithm or Remez algorithm approximation. The time we have to use the low pass, high pass, band stop, multiband, or arbitrary magnitude, and so on. In Matlab, may need to use Hilbert switch for some filters. Example, even length high pass are H pre maz dot m. Yeah, okay, it is the built-in function like this. You should follow, and the following are easy to design with the slight modifications to the algorithm. How we are modifying this algorithm with our what you call our desirability. Okay, what is our desirability? Our desirability is optimum. Okay, optimum by using this different types of the filters. Yeah, these filters generally have zero response near DC and Fs by 2. This is one differentiator h of f is equal to j2 into pi f. Okay, so Hilbert transform is followed by h of s is equal to minus j sin of f. Okay, coming to the differentiator, the differentiation corresponds to the filter h of f is equal to j2 into pi f. The inverse transform of this filter is what you call the first three terms of this response are minus 1, 0, 1, which is the standard approximation. Okay, for differentiation learned in the calculus already we learned. Okay, central finite difference. Okay, the spectral response of this truncated filter is, okay, in the design we generally specify a bandwidth over which the filter acts as a differentiator. Like the inverse transform of this filter is h of n is equal to minus 1 power n 1 by n not equal to 0. Okay, like after applying this all are the spectral response of this truncated filter is, okay, in the design we generally specify the band. Okay, h of z is equal to z power plus minus z power minus 1, h of f equal to e power plus j 2 pi f into e power minus j 2 pi f is also equal to 2j sine of 2 pi f, which for the small f is approximately h of s approximately j 4 pi f. Yeah, this is the impulse response of differentiator. Okay, next Equiripple design. The least square criterion of minimizing. Okay, this is it is not entirely satisfactory because of while using this one, a better approach is to minimize the maximum error at each band. Okay, where epsilon is equal to maximum omega, but what you call e of omega. Okay, it is specified. Equiripple design, the method is optimal in a sense of minimizing the maximum magnitude of the ripple in all bands of interest. The filter order is fixed while you are using the Equiripple. If it is variable, we are unable to what you call ripples are not what you call investigate, or we are unable to justify these all ripples. Is the equal ripple. That's why the filter order is fixed while you are designing this Equiripple design. Yeah, it can be shown that this leads to an Equiripple filter. Okay, the filter which amplitude response oscillates uniformly between the tolerance bounds of each band. Okay, like here that minimum SD into maximum omega E of omega. Yeah, that Equiripple results we will expect like this by the piece of code like Matlab, pass band and stop band. Here it is the many ripples achieve the maximum permitted amplitude. Okay, so overall and passband only frequency response of length if it is 37, okay, minimax filter is observed. More than that, if it is length is 10 or 11, easily you can verify that how it is equiripples are different or changes and so on. Now coming to this one more what you call optimal method. The method is Remez method. So while we are using the what you call non-recursive filter, response is always errors should be minimized. The time we require optimal. That optimal measure one is Remez method. There exists a computational procedure known as the Remez method to solve this mathematical optimization problem. There are also exist formulae for estimating the required filter length in the case of low pass, high pass, and band elimination and so on. Okay, band pass, narrow transition bandwidths. Okay, and however, these formulae are not always reliable, so it might be necessary. Okay, so iterate the procedure so as to what you call satisfy the design constraints. That's why always there in the Remez method or Remez approximation method. So there exists a computational procedure, Remez method, to solve this mathematical optimum problem. The problems are depending upon there are also exist formulae for estimating required filter length, like using the low pass, band pass, and narrow transition bandwidths. Okay, these formulae are not always reliable, so it might be what you call necessary to iterate the procedure so as to satisfy the design constraints. Okay, Equiripple design weights. The weights can be determined in the advance from the Minimax specification. Already we have seen that Minimax, how it is specified. Okay, that specification, say for example, if a simple low pass filter has a requirement for the passband gain to be in the range 1 delta p to 1 plus delta p, and the stop band gain to be less than delta s. Okay, so the weights, the weighting given to the passband and stop band error would be delta s and delta p respectively. These are the depending upon all weights. Weights can be determined in the advance from the Minimax specification. The specifications are passband gain to be in the range 1 minus delta p to 1 plus delta p. Okay, the weighting given to the passband and stop band errors would be what you call delta s and delta p. Okay. The detailed algorithm is beyond the time, the constraints of this particular module, it is all are depending upon FIR, finite impulse response, non-recursive filter, with if it is number of errors are increasing or decreasing. Based on that, if we are using the windowing technique, beyond that, our frequency sampling and so on, the detailed algorithm will be applicable with using the different methodologies, windowed or other thing. This is graphical representation. Response must not entire shaped receive, where delta s, delta p, and so on. Normalize frequency and so on. Equiripple design. So what we'll do that one some simple example for user can understand that how it is varies. Equiripple design or maybe numerical or list example. For this case, for obtain the coefficients of an FIR low pass digital filter to meet these particular specifications, like Passband 8's frequency 1.625 kilohertz. Passband peak to peak ripple 50 decibels. The sampling frequency 8 kilohertz. The passband ripple corresponds to plus or minus 6%, while the stopband attenuation is 0.32%. Okay, hence the weighting factor are set to 0.32 and 6. Okay, with this order is n is equal to 25.8. So that order is, we have to round up this, round figure is 26, where capital N is equal to 26. Hence capital N is equal to 26 are chosen. That is, length is 27. Okay, so now this proved to be substantially too short, and it was necessary to increase the order to 36. Length is 37 to meet the specification, given specification like this. Okay, so you will write that Matlab program for FIR filter Equiripple design. Using the term Matlab, you should follow that where M, where B is equal to Remez of N comma F comma M. This is the design and nth order finite impulse response crystal filter, and return the filter coefficients, the length n plus 1 vector B. Vectors F and M specifies the frequency and the magnitude breakpoints as for FIR2, where B is equal to an image of N comma F comma M and W uses vector W to specify weighting in each of the pass and stop band in vector F and M. Okay, so note that again the frequency normalization, the call which finally made the filter specification. Otherwise, we will unable to expect the response at the time where H equal to Remez, like using the previous that specification, the resulting what you call the Remez 36 0 1.625 or 24 by 4 1100 0.326 and 0.32 and 6. The resulting frequency response is as shown, or we have verified previously. Equiripple, like using this piece of code, we will expect this response. Yeah, using this all above filters are required for optimize after the finite impulse response. The time, why don't you mix that Remez as well as Parks-McClellan algorithm? That's why we can form. Using this previous all stuff, we require for expecting output response with optimum. That purpose, we can mix that Remez exchange algorithm with the Parks-McClellan Remez exchange algorithm. That's why it is formed. The Parks-McClellan Remez exchange algorithm. Here, the computational procedure, the optimization problem is by particular Remez. The algorithm in common use is by Parks and McClellan. Yeah, the Parks-McClellan Remez exchange algorithm is widely available and versatile. With this, so it is important, it is design linear phase. Linear phase is nothing but a symmetric filter, or you can consider anti-symmetric. So based on the symmetric and anti-symmetric, that a finite impulse response is decided. Filter of any of these standard types. One is linear symmetric filter. You can follow the frequency response of the direct form finite impulse response filter. May be rearranged by grouping terms involving the first and last coefficients, the second and next to last. Like this, it is assigned h into exponentially j omega is equal to the summation k equal to 0 to capital M. The coefficients bk e power exponentially e power minus j k omega. This is the first and last coefficient. It is mentioned. This is the first coefficient and last coefficient, and so on. Then take out to common factor for this one. Finally, we will expect that response. So based on that, if the filter length is m plus 1 is odd, then the final term in curl braces above in the single term b into m by 2, that is the center coefficient tab of the filter. Okay, and the symmetric impulse response, symmetrical impulse response, if we put bm is equal to b naught, bm minus 1 is equal to b1, etc. Note that exp of j theta plus exp of minus j theta is equal to 2 cos theta. The frequency response becomes like this: h into exponential of j omega is equal to 2 exponential of minus j m omega by 2. And to first component b naught, okay, that b naught cos of m omega by 2 plus next coefficient b1 plus b1 into cos of m minus 2 omega by 2 plus b2 cos m minus 3 and so on. Plus like this, symmetric impulse response will be appeared. The frequency response becomes like this. Yeah. This is the purely real function sum of the cosines multiplied with a linear phase term. Hence, the response has a linear phase corresponding to the pure delay of the m by 2 samples, that is of the filter length. Okay, a similar argument can be used to simplify antisymmetric impulse responses in terms of sum of sine functions, such as filter do not give the pure delay, although the pass or maybe in terms of the phase still has a linear form pi by 2 minus m over 2. There is implementation of symmetric finite impulse response filters. That implementation, the symmetric FIR finite impulse response filter of length is n can be implemented using the folded delay line structure. The structure is, we have seen, check it here, which uses of n by 2 or n plus 1 by 2 multiplies rather than n. Like this, x of n. So on, given that the coefficient b of n minus 1 by 2, and we will export the output response. The symmetric FIR filter of the length n can be implemented using the folded delay line structure as shown in this figure. So xn is given to that, b naught will be observed, b of n minus 1 by 2, that we will export delta by, which uses n by 2 or n plus 1 by 2 multiplies rather than capital N. There is a limitation of this particular algorithm. So linear phase in the stop band is it's never a real requirement, and in some applications strictly linear phase in the pass band is not needed. Either a linear phase filter designed by this method are therefore longer than optimum non-linear phase filter. This is the major limitation where you are using this type of algorithm for optimum level. However, symmetric finite impulse response filter of length n can be implemented using the folded delay line structure that we have seen. Okay, so which uses n by 2 or n plus 1 by 2 multiplies rather than capital N. Okay, like this, the limitations of the given algorithm will be applicable. So the longer symmetric filter may be no more computationally intensive than shorter nonlinear phase one. Compare that limitation of this symmetric FIR filter of length n can be implemented using the folded delay in the structure based on this structure, say n by 2 or maybe n plus 1 by 2 multiplies rather than the capital N. So the longer symmetric filter may be no more computational intensity than the shorter nonlinear phase one. Okay. Yeah, like this, ready to use. These are optimum filter. Okay.
Like, share and subscribe. Hit the bell icon for more updates.